Welcome viewers to the second segment of the second lecture for the online series of lectures for the course of linear algebra. In the previous segment, towards the end, we proved a theorem which stated that equivalent systems of linear equations admit the same solutions. Now in this segment, we'll start discussing elementary row operations. Elementary row operations, abbreviated as ERO. Okay. So, expressing an equation of a system as a linear combination of equations from another system may turn out to be very cumbersome. As one sees while working with the simple systems introduced in the exercises, suggested earlier in the earlier segment. Okay. So for this reason, one defines elementary row operations. As below. Okay, so we need some notations. So consider the system of linear equations 1. Okay, let me write it for you if you don't recall it. It was a11 x1 plus all the way up to a1n xn, which was 1 y1. Then the second equation was a21 x1 all the way up to a2n xn is equal to y2, and the mth equation of this system was am1 x1 plus all the way up to amn xn is equal to ym. Okay, and here one can write this system as, so let me erase everything here. One can rewrite this system of linear equation as a matrix equation like this, where A is called the matrix of coefficients, which is an m times n matrix given by a11, a12 all the way up to a1n, the second row being a21, a22 all the way up to a2n, and finally we have the mth row of this matrix of coefficients to be am1, am2 all the way up to amn. Okay, so this is called the matrix of coefficients, the matrix of coefficients. Okay, this is our A, and X is a column vector, which is an n times 1 matrix. Those entries are x1, x2 all the way up down to xn, okay? And y is also a column vector, which is an m times 1 matrix. The entries being y1, y2 all the way down to yn, okay? And one can immediately check that if this matrix, this m times n matrix, gets multiplied with this n times 1 matrix, and we set the resulting m times 1 matrix to set that resulting m times 1 matrix equals to this m times 1 matrix, one precisely gets this system of linear equations. Okay, check that. And here, this matrix, this is a variable n times 1 matrix, or a column vector, because this is actually the matrix or the column vector of unknowns. And this matrix of coefficients, and this matrix, this m times 1 matrix or this column vector, have entries from the given field F. Okay, so A and Y are m times 1 and m times n and m times 1 matrices respectively over the field F. Okay, so now we give the formal definition of elementary row operation. Okay, now that we know how to write down a system of linear equations as a matrix equation, we define elementary row operations. Operation definition. An elementary row operation is a special type of function denoted by E that associates each m times n matrix and m times n matrix E of A in the following three possible ways. Okay, so it means that it's a function on the space of m times n matrices. Okay, A is an m times n matrix and E is a function acting on this space of all m times n matrix, and the resulting matrix E of A is also an m times n matrix over the field F. Okay, so one, E of A, the final matrix, okay, the ij entry of that matrix is going to be equal to the ij entry as long as I is not equal to R, okay, and E of A Rj is equal to C times Arj, okay. Here we want C to be not equal to 0, okay. So it tells us that we were given an m times n matrix, and there was a given row of that matrix, and the elementary row operation was actually to multiply all the entries in that row with this non-zero scalar c, okay. So in words I write it as multiplication of a row of the matrix A by a non-zero scalar, and we all know that the scalar means element from the field F C. So that's the first possible elementary row operation. The second one tells us that E of A ij is equal to Aij as long as I is not equal to R, and E of A Rj is equal to Arj plus C times Asj, okay. Here we so I write it in words. It means that replacement of the rth row of the matrix A by row R plus C times row S. Here C can be any scalar from the field F, and R is taken to be unequal to S. Okay, the two rows under consideration should not be equal. Okay. Okay, so the third operation is that of interchange of two rows of the given m times n matrix A. It tells us that E of Aij is equal to Aij as before if I is not equal to R, and of course we also want I to be unequal to S, and E of A Rj equal to E of A Rj is equal to Asj, and E of Asj is equal to Arj. In words, it's just the interchange of two rows of A, the rth row and the sth row. They are interchanged between them. Interchange of the rth and sth row of A. Okay, all right. So this is how this function A to E of A is defined. Okay. Okay, these are the three basic types of elementary row operations. Okay, so let me erase everything. We have our second theorem. It states that to each elementary row operation E, there corresponds an elementary row operation E1 of the same type. So there are three types discussed earlier. Okay, so E1 of the same type, that is E and E1 belong to the same type as E, such that E1 of E of A is the same as E of E1 of A is equal to A for each A in the space of M times N matrices over the field F. In other words, the inverse operation, which is of course a function, since the original operation was a function, the inverse operation of an elementary row operation exists. It always exists, okay? And is an elementary row operation of the same type. This is what we need to prove, okay? Let us prove it. So, we prove the result stated above for the three basic types of EROs separately. Okay. Okay. So let's consider the first type. Okay. For the first type, where the elementary row operation was to multiply a single row of the given matrix A by a non-zero scalar C. Okay, that was the first type. So for this type, define this matrix E1 by E1 of A I j is equal to Aij if I is not equal to R, and E of A Ij is equal to C inverse, E of A Rj, okay, when I is equal to R. Okay, for this case, E of A Rj is equal to C inverse A Rj. and C is non-zero, meaning that C belongs to the field set minus this zero element. So this is how we are defining this elementary row operation E1. Okay, now check that E1 of E of A. So Ij, okay, is E of A. We are using this definition, E of Aij. In this case, we just replaced A with E of A. Okay, so E of Aij, and which is equal to, by this definition, A of Ij if I is not equal to R. And using this part of the definition of E1, we see that E1 of E of A Rj, so we are using this definition, okay, and here we are taking E of A for A, so this is going to be C inverse E of A Rj, right? You can put everything inside this bracket, right? And by the definition E of Arj, the one that is given here, we have, sorry, this is E1, okay, right? And by the definition of E, okay, I did not write the definition of E, so remember that the first type was E of Aij is equal to Aij, right, for I is not equal to R, and was E of Arj was equal to C times Arj, and C was taken to be non-zero. Okay, so using that definition of the first type of elementary row operation, so we are writing it like this: E of Rj is equal to C times Arj, right? And this is Arj. Okay, so let me repeat: E1 of E of Aij is equal to E of Aij using this definition, and E of Aij is equal to Aij using the original definition of this type, where I is not equal to R. Okay, and E1 of E of A Rj is equal to C to the minus 1 times E of Arj using this part of the definition of E1, and E of Arj is equal to C times Arj using the original, this part of the original definition of the type 1 of elementary row operations. And now C inverse cancels out against C, and we are left with just Arj. So we have seen that E1 of E of Aij is equal to Aij if I is not equal to R, and we also have seen that E1 of E of A Rj is equal to Arj. What does that mean? It means that E1 of E of A is equal to simply A. Okay, similarly one can show that E of E1 of A is equal to A. For type 1 elementary row operation E. For type 1 ERO E. Okay, so we are done with the first type. So let me erase everything and move to the second type. For this type, define E1 by E1 of Aij is again the same as Aij if I is not equal to R, and E1 of A Rj is equal to Arj minus C times Asj, where R is not equal to S and C is any element from the field F. Okay, so these multiplications are well defined. You see that these are multiplications in the field. Okay, so this is how we are defining our E1. Okay, let us recall that for the second type, the operation E, the original elementary row operation, the basic type of elementary row operation was defined as follows. E of Aij was the same as Aij when I is not equal to R, and E of A Rj was Arj plus C times Asj, where R was taken to be unequal to S and C was any scalar. Okay, this is how the second type of elementary row operation was defined. Okay, so now check that E1 of E of A, so like we did in the case of first type, Ij is using this definition is E of A Ij, and E of Aij is equal to Aij, right, when I is not equal to R, and E of A, E1 of E of A Rj, right, is equal to, now we are employing this definition. So we're just replacing A with E of A. Okay, so everything here should be replaced with E of A. A will be replaced with E of A. So it's going to read E of A Rj, and it has to read E of C times E of A Sj. from the definition of E1, okay, for the second type. And E of A Rj from the definition of the second type of elementary row operation, we know that this is equal to A Rj plus C Asj. Okay, and this is simply C times Asj. Okay, this we can write as Asj using this, okay, because S is not equal to R. Okay, so it follows, since E of A Sj is equal to Asj, as S is not equal to R, and this formula holds. So this is simply Arj. So we again have seen that E1 of E of A is equal to A. And one can go on to prove that E of E1 of A is equal to A for this second type of elementary row operation. Okay, for the third type, define E1 of A Ij is equal to A Ij for I is not equal to R and I is not equal to S, and E1 of A Rj equal to A Sj and E1 of A Sj is equal to Arj. So in other words, we are taking E1 to be exactly equal to E. The two operations are the same. So E is the so E is an elementary row operation of the third type, and E1, its inverse, is taken to be equal to itself. Okay. Now see that E1 of EA Ij is simply equal to E of A Ij, and we know that E of Aij, because E1 and E are the same, E of Aij is also Aij for I is not equal to R and I is not equal to S. Okay, and E1 of E of A Rj is equal to E of A Sj, right? From the definition of E1, which is exactly the definition of E. and E of A, sorry, should write it like this, E of A Sj, and E of A Sj is simply Arj, right? And E1 of E of A Sj is equal to E of A Rj, and E of A Rj is A of Sj. So which proves that combining these three results, we immediately see that E1 of E of A is simply equal to A. Now it's obvious that since E1 and E are the same, it's obvious that E of E1 of A is also equal to A. Okay? Okay, so this way we are done proving theorem 2, QED. Now we have a definition, a new definition of row equivalence in terms of elementary row operations. Okay, we previous equivalence was equivalence of two systems of linear equations. Okay, which we called equivalence of two systems of linear equations. Now the notion is about row equivalence of two matrices. Okay, two m times n matrices over the field F. Definition: if A and B are m times n matrices over the field F, B is said to be row equivalent to A if B can be obtained from A by a finite sequence of elementary row operations. Okay, so this is the definition of row equivalence between two matrices. Okay, now we have our third theorem, which tells us that if A and B are row equivalent m times n matrices over F, the corresponding homogeneous systems systems of linear equations Ax equal to 0 and Bx is equal to 0 have exactly the same solutions. Okay. So now this theorem establishes the connection between the two equivalents that we have defined in this lecture. One equivalence was the equivalence of two systems of linear equations, and the other equivalence is the row equivalence that we have just defined between two m times n matrices. Okay, now let's get back to the proof of this theorem, theorem 3. I need space and therefore I erase everything. Let me erase everything. Proof. Okay, suppose we pass from A to B by a finite sequence of EROs, by a finite sequence of EROs. Okay, so let me put a small diagram to denote it. So the initial matrix is denoted by A0, which is just A, and we do finite sequence of operations to, to change it first to A1 and then to A2, and on at the kth step we recover AK, which is the same as B. Okay, so after these k elementary row operations, or probably k elementary row operations, we get B. Now it's immediate that it's enough to prove that a jx is equal to 0 and a j plus 1 x is equal to 0 have the same solutions, meaning that it's enough to show that while passing from A to B, if we take two consecutive elementary row operations, and then the matrices, the corresponding matrices that we have, okay, one is AJ and the other one is AJ plus 1. Okay, for these two matrices we get uh, homogeneous system of linear equations, and these two homogeneous system of linear equations have the same solutions. It is enough to show this, because if we have this, then by induction one can prove this immediately. Okay, so this you know it, it, suppose that B is obtained, so it means that it is sufficient to prove this case for a single elementary row operation. Okay, and for this we suppose that B is obtained from A by a single ERO. So irrespective of EROs performed, each equation in the system Bx is equal to 0, will be a linear combination of the equations in the system Ax is equal to 0. Okay, so we take for instance the second type of ERO. For instance, take the second type of elementary row operation. Okay, so B is obtained from A by a single elementary row operation, which is of type 2. Okay, which means that Bij is equal to E of Aij, which is equal to Aij if I is not equal to R, right? And this situation can be described in terms of rows in the following way. So it means that we are taking the ith row, which is not equal to the rth row. So I is anything except for R from 1 to m. Okay, so we taking the ith row, which is bi1 all the way up to bin. So it is equal to the ith row. Okay, so which we can write as 0 times the first row of A, which is A11 all the way up to A1n. Okay, now 0 times the second row of A, which is A21 all the way up to A2n, and then you have the ith row, right, which is 1 times the ith row is AI1 all the way up to AIN plus finally one has 0 times the mth row of A. Okay, AM1 all the way up to AMN. Okay, so this is how you write the ith row of B as a linear combination of the various rows of A. Whenever I is not equal to R. Now let me erase this part, top part, to create some room. Now if also remember that for the second type of elementary row operation, Brj, by the definition, B is equal to E of A, so Brj is equal to E of Arj, and E of Arj is equal to ARJ plus C times ASJ, where S is not equal to R and C is any scalar. Okay, so here, so we are concerned about the rth row of B now, which we write as BR1 all the way up to BRN. This is equal to 0 times the first row, A11 all the way up to A1N, then 1 times the one from the field F. Okay, 1 times the rth row of AR1 all the way up to ARN. This is the rth row of A, plus dot 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 C times the sth row of AS1 all the way up to ASN, right? Plus dot 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 0 times the nth row of A. So in this linear combination, two non-vanishing contributions from the rows of A are, from the rth row and from the sth row. Okay, so this is how you see that the rth row of B can also be written as a linear combination of various rows of A. Okay, therefore it tells us that each equation of the system Bx equal to 0 can be expressed as a linear combination of the equations in the system Ax is equal to 0. Okay, if B is equal to E of A with E being of type 2. Okay, this is what we have shown. Okay, and now this result can be shown to be to be held for the other two types of elementary row operations as well. Okay, so we have shown that each equation of Bx equal to 0 can be expressed as a linear combination of the equations in the system Ax is equal to 0. Now we have to show that each equation of Ax equal to 0 can also be expressed as a linear combination of the equations in this system Bx is equal to 0. This is the goal now. Okay, let's do it. Okay, now If B is equal to E of A, with E being one of the three basic types, one of the three basic types of EROs, one of the three basic types of EROs, then one immediately sees that A is equal to E1 of B, where E1 is the inverse elementary row operation, inverse ERO, described in theorem 2. Okay, so why is it the case? Because E of, so if you plug in A here, you immediately see that you get B back. Okay, meaning that E of E1 of B is equal to B. This is why this holds. Okay, you can always find this, the inverse operation E1. Okay, so it tells us that A can be obtained from B by an elementary row operation, which is E1. Okay, A can be obtained from B by an ERO. Okay, so therefore, using the arguments presented above, for this way, okay, these things, this is what we have done before, and using these arguments again, one can show that each equation of the system of the system Ax is equal to 0 can be expressed as a linear combination of the equations in the system Bx is equal to 0. What we were looking for, right? Okay, so together this and this, okay, we immediately see that each equation of the system Bx equal to 0 can be written as a linear combination of the equations in the system Ax equal to 0, and each equation of the system Ax equal to 0 can be written as a linear combination of the equations in the system Bx is equal to 0. Okay, and hence by theorem 1, the two homogeneous systems Ax is equal to 0 and Bx is equal to 0 have the same solutions. Okay, QED. Alright, At this stage, we take a break, and we'll be back with some examples in the third segment of this lecture, of this second lecture. Okay.